I'm always happy to come back to Stockholm because so many of the important collaborative studies over the years have involved Swedish scientists, so it's very exciting to be back here. So today we're going to share with you some of the most recent data on baby brain development and what it has to do with one of the most important things that humans do, and that is that we have the capability to communicate, to speak to one another, to create poetry and fabulous books. Language is one of the windows, I think, on the human mind, and it starts here. How is it that children all over the world, from the birth on, when you hear the initial cries, to creating the sentences that wow us at age 2 and at age 3. At age 3, any child on the planet can talk your leg off. They are just very, very capable of producing novel thoughts, and this is your path to communicate with them. So it's a very, very exciting time. What we've added in the past decade is the ability to image the baby brain. I'll show you more studies as we go along here. This is a very young baby in a magnetoencephalography device, $2.5 million, very big machine. And I'll show you what you can see that you can't know in any other way by looking at the baby brain while they're listening to a word or looking at the face of their parent. So brain function gives us a movie of the activity in the brain structure through MRI, and very sophisticated measures now of the areas and pathways, the connecting pathways in the brain, so we can link activities and growth in particular areas to the microstructure of the connectivity within the brain of a baby. And the combination of the brain function and brain structure measures is really exciting. Also today, I'll show you a little bit, we've dipped our toe into the study of genes related to language learning. So we have just one study published in 2016 linking brain behavior and genes. And so it shows the exciting new frontiers that we're crossing to try to understand all the components of learning. So as I said, I think that language is a window on the way brains learn, on this combination of nature and nurture. And I think it gives us a very unique opportunity, and particularly when you can watch from the beginning. The interesting thing about language is that you can vary the conditions under which kids are born. So you can study in Stockholm and study in Asia and study in the United States. The kids who are growing up listening to different languages, you can measure right from the beginning what's the initial state of knowledge about language. You can do cross-species comparisons. There's so many things that you can do as long as you use a level of language, not sentences, but as I'll show you, looking at the phonology, the phonetics of language, the sounds, consonants and vowels that we use to make words. So you have the opportunity, there's great traction on this topic at that level to make these interesting comparisons. Well, here's something that everybody agrees on, and that is that language exhibits a critical period for the acquisition of a second language. So that's what's plotted here. If you find your age at the bottom and you look at the vertical axis, you'll see how good you are at acquiring a second language with ease and with thorough, complete learning. And you'll see from that graphic, it's a cartoon, but the graphic is composed of studies that have done by many, many laboratories over the years, demonstrating that between 0 and 7, the children are geniuses that acquire a second language. They're virtually, identical to the primary, the first language that they learn. But that every 2 years after the age of 7, there's a decline in the native ability to acquire that second language, and after puberty, there's a dramatic shift in your ability to acquire. And so the question is, why? What's stopping learning beyond a certain age? And what's the magic that young infants put to work that we can't put to work anymore? The other reason it's important to look at that initial period is that's when all of the disorders regarding language, so autism has a huge language component, specific language impairment, dyslexia, all of these things take hold, Fragile X, they all have impact, negative impact on language. So understanding how it really works may allow us to get in with early biomarkers of those risks and then apply very interesting interventions based on what we know about learning that can help these kids. Also, the effects of socioeconomic status on language. That early period turns out to be extremely important. studies have shown that brain development depends on these early social experiences. So children coming from families that are in poverty, or parents without a good education who don't think it's important to talk to children early, you can see the impact on the brain by age 5. So it's very important to understand what's happening, and maybe perhaps even for us, the adults of the species who want to learn a second language, what are the tricks that we could try to apply so that our learning can be as rapid as that of an infant. So within the big picture of critical periods, there are smaller ones. So this initial learning about the sounds that your language is going to use happens very early in development, and that's what we're going to focus on. That window of opportunity is the one we're going to look at today. But a little bit later, around 18 months, so under a year, is when that initial sound learning occurs. Then at about 18 months, word learning explodes. And then at about 24 months, grammar learning explodes. So you can see these various windows of opportunity. We're going to focus on the first one, having to do with the sounds. So let me tell you a little bit about the sounds of language. So look at first the top of this graph. You see the physical arrangement of the phonetic unit ah on the left and ah on the right. Look at the tongue shape. So if you go ah, ah, you'll see that your tongue moves. And below, you see the physics of the situation, the formant frequencies. So you play a note on the piano, various notes can produce a chord. These formant frequencies are like chords. It's your vocal tract processing and enhancing certain frequencies that allow you to hear ah, ah. Now, the variability think of the mouth variability just in this room, and then think of children and adults and how males and females, the oral tract differs. Machines struggle with speech recognition because the recognition of what's an ah, those frequencies change all over the place. And languages vary which categories are important. So many languages, Spanish for example, combine ah and ah into a single category. That distinction doesn't matter in Spanish. It does in English. Pot, pat differs on that particular sound. So let's just listen to a variety of people producing that sound ah.
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 You learn a lot by listening to, whether it's male or female, young or old, those same people producing ah.
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 Ah. Ah.
Ah. Ah.
Ah. Ah.
Ah. Ah.
Ah.
Okay, so artificial intelligence has struggled with this categorization problem, whereas humans, even babies, have no trouble with this. From the beginning, they can hear these differences between the two categories and across all these variations. And we know that because we've set up experiments where we train babies. This is a behavioral task I've done in at least 8 different countries. About 15, 20 years ago, I had laboratories, behavioral laboratories, in about 8 countries in which we had babies sit on their parents' lap and be distracted by a toy on the right while sounds were coming out of the left. And we could vary. So, for example, I'll show you a movie where the baby's hearing ah, ah, ah. And the baby's job is to detect when it changes to another sound of language. And if they turn their heads at the right time, they get a big reward. So here's how that technique works.
Can a baby as young as 6 months old hear the difference between 2 vowels? This baby is trained to look for the toy when the sound changes. She's being distracted, so she'll turn only when she hears the difference in sounds. The key question, will she turn before the toy lights up?
E. 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 E.
Okay, so it's a very smart baby, but they're all that smart. So any place on the planet, you do these tests with babies at 6 months, and they can all be trained within 20 trials to turn their heads. So the key thing is, what distinctions can they hear? These are micro changes in frequency and time. They're difficult. They're not the simplest thing. You could have imagined that it takes a while for babies to hear these differences, when in fact the studies across countries show that infants in any country, regardless of the sound contrast that you used, can hear all these distinctions and turn their heads appropriately. The mothers and fathers sitting in back of them cannot. So the mothers and fathers sitting in back of the babies can only hear the distinctions of the language they were exposed to in the first 7 years. So they are culture bound, but the babies are universal citizens of the world. They can hear them all. And so that was a major finding, that we're seeing these differences in infants and in adults with regard to their capability. But not only is this, difference between adults and infants important, there is an important finding about when. If you had to guess, when is a baby going to change from that citizen of the world that they start out to the culture-bound behavior that you and I exhibit as adults? And the answer is extraordinarily early. They make that shift before their first birthdays. Okay, before they turn 1, and that's when kids learn their first words, this whole business about which sounds does my language use has all been sorted out across these cultures. And that's important. So here's one of the graphs from one of the studies we completed. Here's a study on American infants in Seattle and Japanese infants in Tokyo. And we're testing them on a contrast that's important to English but not Japanese. So ra, la, as in rake, lake, or read, lead, very important to English word distinctions, but not at all important to Japanese. It's ignored in the Japanese language. It doesn't matter. Japanese people have a terrible time trying to discriminate between R's and L's, both in speech production and in speech perception. But you can see what the babies do. At 6 to 8 months, everybody's equivalent. The Tokyo babies and Seattle babies, perfectly able to make the head turns way above chance, about 65%. And then 2 months later, between 8 and 10 months, a miracle happens. The American kids get a lot better at it. Japanese kids go down basically to chance. And in both cases, the kids are doing exactly what they need to do to acquire that language. We want babies in Japan to ignore that distinction. We want babies in America to uphold that distinction. This we found all over the world. This is what's happening. Native sounds and non-native sounds. So that magical period got to be very interesting to a scientist. What's going on between 8 and 10 months? How do they do this? And we illustrated not only with behavior, but brain measures. About 15 years ago, we started doing event-related potentials. The same kind of design. The baby's listening to a sound in the background like rah, 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 and the standard waveform is what you see in the EEG waveform. And then when you switch it, rah, 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 la, you get this deviant response, which is that negativity, known as the mismatch negativity. So behavior brain looks exactly the same. What's interesting is that this ability to learn between 6 months and 12 months predicts language growth to 30 months and reading readiness at age 5. It's a really important first step in acquiring a language. We showed that by looking at the event-related potentials at 7 months, so that's really early. At 7 months, some kids have already made the switch. They've already started learning, showing better responses to native than non-native, and some kids haven't. So what you see plotted here in A is a baby wearing an EEG cap with the electrodes, and in B you see this baby's response to native, big dip in the red line. So you see this baby, let me see if I can turn this on. Let's see, where? It was on. Well, anyway, where's the button? Oh, here it is, got it. So when this baby listens to a native English sound, look at that deviant, big response to the native, and already ignoring, essentially, not attending to the non-native, whereas earlier this baby was shown to discriminate both. If you divide the children into the top half of the distribution, a median split, the kid's better at native and as opposed to non-native. This is the growth curve of words from 14 months to 30 months. The kids who are better at native discrimination zoom up faster in language growth. Kids do just the opposite for the non-native predictor. The better a baby is at discriminating non-native contrasts at 7 months, the slower their language acquisition. So it's pointing out that in monolingual babies, attending to the right stuff in your environment, recognizing what sounds to lock onto, really assists the growth of language. It was the first finding linking speech to language, showing that early speech predicts later language. And so this initial learning, so we know from this result that it's not, hearing acuity. If it was hearing acuity, babies, regardless of whether it's a native or non-native sound, the better they were, the faster the language would grow. It's not about acuity, a sensory ability. It's about the ability to learn, and that's what was demonstrated. So I want to dip back now for a second to a finding from 1975, just because it's a benchmark. My first study, basically, was to compare babies and animals, in this case chinchillas and later monkeys. The question was whether these boundary effects, so this is a graphic of a computer difference, a change from ba to pa on a continuum. So on one end of the continuum you hear ba, the other end you hear pa, and small changes in between. Adults don't hear the changes in between the category. They only hear it at the boundary. It's like a sharpening of discrimination between the two categories that assists your ability to listen to words quickly and understand what they are. Peter Imus in 1975 was the first to demonstrate that babies were better at discrimination here. So for equal differences in this part, within a category, or right at the boundary, human infants are better right at the boundary. So I tested whether that was is that a human exclusive ability or not, and demonstrated in both chinchillas and in monkeys that there's a heightened discriminability for mammals listening to speech that matches the one shown in humans. Doesn't say that animals can form categories or do sophisticated learning with regard to speech, but this initial partition of the sound spectrum at a place on that continuum, a kind of basic break, is something we inherited in evolution. It's like language took bits and pieces from different aspects of our cognition, different aspects of our sensory systems, and in the invention of language capitalized on this effect. Now, for those of you who know the history of linguistics, you know that this was not a popular finding at the time. It was not considered something people liked to hear, that chinchillas and monkeys could form this perceptual break on the continuum. Now here we are many, many decades later, and of course it's been embraced that language and evolution, that there's an evolutionary path towards language. But at the time, you have to stick to it. Students in the audience, stick to findings you know and believe in, that they will eventually be proven to be correct. So this is the biological formation, this is the biological contribution to what babies are doing. They can separate things in the appropriate way, and that's good. But there's something more powerful going on as they are learning. So across this boundary from 6 to 12 months, they start out hearing all the distinctions. Eventually, to learn, they have to focus on the right ones. And so we've learned something about what's going on in that 8 to 10 month period, and there's two components. One's highly computational, and one is highly social. So the initial learning, I'm putting this slide up because it's a collaborative study that Christine Moon from my lab and Hugo here in Sweden and myself published in 2013. So we took a series of stimuli that had, I'll show you them in a second. We had demonstrated that by 6 months of age, babies have learned from listening to the sounds in their culture. But what Hugo and Chris and I showed is that even newborns, so we were in the Stockholm newborn nursery and in the Seattle newborn nursery, and we showed that babies at birth in the newborn nursery within 2 days of being born would, when presented with sounds from Swedish and English, they would prefer the non-native language, the novelty. So the last 10 weeks of pregnancy, babies are listening, they can hear, and they've been hearing mother talk. And they've learned enough about the sound structure that the contrasting vowel is exciting. They will suck on a nipple to turn it on. So learning starts powerfully even before birth. But by 6 months, the learning is sophisticated. So in a papers published in Science, again, a paper published with our colleagues here, Bjorn Lindblom is on this paper in Science 1992. We showed that in the head turn task, if you present babies in Stockholm and in Seattle with a variety of vowels around the English prototype E and a variety of vowels around the Swedish prototype U, that babies will go further before they hear it change. From that prototype in the middle, it takes a long while before they hear it change. They've already begun to form a category simply by being in their cribs in either Stockholm or in Seattle and listening. And here are the results of that study. So American infants showed high generalization around the prototype in English, but not around the Swedish vowel. And the Swedish babies here in Stockholm showed high generalization around the Swedish vowel and less around the American English vowel. So by 6 months, the babies have learned quite a bit just by listening to us talk. And we know a little bit about the mechanism. So it turns out that babies have great statistical learning capability. And what I mean by that is that they're affected by what they see and what they hear and what they feel. They can develop a kind of distributional sensitivity. They are sensitive to the frequency with which they hear and see things. And we can, again, illustrate that in a cartoon fashion by listening to a woman speaking English motherese and then Japanese motherese. Motherese is that high-pitched, very sing-songy signal that parents produce uniformly across the world and kids love. So here's what parents in speaking English and Japanese sound like, and then I'll show you what the babies are doing in their own minds.
I love your big blue eyes. So pretty and nice.
うわー、大きな茶色いお目目。そして綺麗な黒い髪。
Okay, so that's a signal that's like mother's milk to a baby brain. The babies are taking statistics, and that we can show in experiments that they extract a kind of distributional cartoon as they listen to sounds. You can create a Japanese listening baby or an American English listening baby by changing the distribution of the sounds that they hear in the laboratory. So if I present an American baby with a unimodal distribution, sounds only in the middle, for 3 or so minutes, what happens is the baby's discrimination of R and L goes down. They behave more like a Japanese baby. If I present them with the Japanese babies with a high bimodal distribution of R's and L's, they will get better at discriminating those two sounds because of their ability to extract statistics as they listen to us talk. But that's not the only thing going on, and we demonstrated that by asking a new question. So if you believe that babies take statistics, and there's every reason to believe that they do, you can ask whether or not they can take the statistics on a brand new language right at that critical moment at between 8 and 10 months. What if you present a baby with Mandarin or Spanish for the first time during that period? And that's what we did. Can they extract the statistics? That was our question. So we had done studies in Taiwan and in Seattle, again, this is Taipei and in Seattle, with a Chinese contrast that to me sounds like she, exactly the same to my ear. But to the Mandarin-speaking kids in the lab, they say, oh yeah, those two are totally different. That's as different as pa, ba. But to me, they were the same. So what we did, this is the result of the study, Taiwanese babies getting a lot better, 10 to 12 months, and American babies getting a lot worse. So it's the Taiwanese babies who, listening to Chinese, will get much better. So during this time, we had an intervention, 12 sessions, 25 minutes each, where the babies heard 4 different talkers speaking to them. And the question is, what will they do? Can they extract the statistics and learn something about Mandarin or not? So here's what those sessions look like.
Jasper, 早安 Finn。嗨，我们要来讲一个故事哦。今天要讲的故事是《小熊七七探险记》。来看看发生了什么事情哦。小熊七七在这里，一个绿色的圈圈，绿色的圈圈，绿色的圈圈，转一下，转一圈，嘿，一圈，再一次哦，转1、2、3。
Okay, so what do you do to that little brain when you present with brand new language at this critical moment? So did the babies learn or didn't they? So we had to run a control group just exposed to English in case coming into the laboratory was so fun they just got better at everything. So the kids who came in and heard the American graduate students in the same way didn't learn anything about Mandarin. I mean, thank goodness, right? So we have an experiment. And here's what happened to the kids exposed to Mandarin for 12 sessions. Their learning was so good, they're statistically identical to the kids from Taiwan. So the answer here is that if you hit the brain with the right stuff at the right time, learning is truly exceptional. They learn amazingly. So our question then was, if they're just taking statistics, wouldn't a machine be just as good? If it just is listening and there's an automatic statistical learning device in the brain of a baby, then the social context shouldn't be essential. So we ran another group of babies with these beautiful DVDs, and the graduate students thought they would learn phenomenally well because they crawl up to it and pay such close attention, touch the screen and everything. Well, what happened? So here's our old graph, and we had run an audio-only group. They were watching a teddy bear on the screen, so we learned audio-only doesn't do anything to Mandarin learning. Here's the TV group, nothing. Zero learning. Even though they were very attentive, they learned nothing. So it takes a social context, takes a social human being at this time in development to learn. And we've now shown in experiments that the eye gaze of the baby predicts the amount of learning. So babies who are, as the tutor holds up a new toy and names it in Mandarin, or later experiments it was Spanish, as the tutor looks at it and names it in that foreign language, the babies who watch her face and this and her face and this and understand that she is referring to this, they learn the best. So social learning skills are correlated very, very strongly, 0.75, with the brain measures of learning. So this social context of learning is extremely important. If you think about the evolution of language, it's not so surprising. Our drive to communicate came from our social need to survive in groups. And so this social learning skills is extremely important. So even for us, I mean, I think we need to think about this in our schools. We need to think about this in terms of our daily lives. In a digital world, we talked a lot about this digital world on Monday at the Swedish Academy of Medicine. It's a very hot topic how much we're in front of machines and how much we've reduced for our adolescents and even our kids, their exposure to in one-on-one social interactions. We can talk about that later. So now, most recently, we've put the little babies in the big machine. So this is a magnetoencephalography machine, $2.5 million. It's important because it makes no noise, perfectly safe, non-invasive. It's not like a clanking MRI or fMRI, where you have to lay still in a tube. We're the first in the world to put little ones in a MEG machine. And this machine is on. You can hear how quiet it is. The baby's listening to sounds from different languages in insert earphones. But the baby's free to move because we're tracking the head. We've got pellets in a cap on the head, so we always know where the head structure is and therefore where the brain structures are. And we can calibrate for movement and then understand what's going on. You get a movie because you can see both the spatial localization very accurately, about 1 millimeter under the best of circumstances, but sub-millisecond. So here's the kind of picture we get. Combining structural and functional, we have structural measures in a 12-month monolingual showing about 150 color-coded areas. We're going to focus on auditory areas and on Broca's area, which is the place where you move. It's your kind of respond. When you imitate speech, you're connecting through the arcuate the ability to hear speech and the ability to produce it. And what we saw in this experiment is that the surprise was the Broca's area and the cerebellum, these motor areas, are very active during speech, and they're not active during non-speech. So there's something about the speech signal that's causing Broca's to act. Even before, we see this, we tested 7 and 12-monthers. Even the 7-monthers are showing very active Broca's area. For 7-monthers, native and non-native, equal activity in auditory and Broca's. By 12 months, there's a heightened activity in the auditory for English compared to Spanish, but what happens in Broca's is it gets stronger. It's as though the motor areas are trying to plan, to simulate, to synthesize. What do I have to do that? How can I talk back in the way that I want to socially? It's a very social response, I think, to see this kind of thing in Broca's area. And it becomes harder for a 12-monther who is now imitating the sounds of the native language to hear a foreign language sound. Broca's area doesn't know how to simulate that. So I think this sensory motor connection is an extremely important thing about human beings. We don't imitate without sensory motor connections. Children don't learn without sensory motor connections. Understanding how this is working is going to tell us a lot about the intelligence of human beings. Here's just the statistical result. At 6 months, you see basically no difference between superior temporal for English and Spanish, and inferior frontal is less, but you can see equivalent for English and Spanish. In 12-monthers and in adults, you see the exact same pattern, that you get higher auditory responses for English, but higher motor responses for Spanish. This V-shaped function is shown in the 12-monther and the adult. We're very curious now to examine the arcuate. This is the connecting tissue pathway between Wernicke's auditory areas and motor areas. Again, we think the growth of this pathway, which is extremely important to reading, is going to be critical. Jason Yateman, if you're interested in reading, Jason Yateman now at iLabs is doing wonderful work looking at the growth of this fiber tract and its relationship to reading. He's got data suggesting that you can detect when it's the best time to teach a child to read. The arcuate is growing rapidly at the time when instruction in reading is the best. But you can also, there can be a time when it's too early or too late for reading instruction. So you can surmise that we're pretty interested here in social and language development. We're doing studies now where mothers and babies are interacting. The baby's in the MEG machine and the mom is in an ERP cap. We're looking at causal networks, the causal models of the kind of behavior change that parents can induce by doing certain things, by smiling, by frowning, by talking, by singing, or by turning away. And we have a study in progress that I'm going to just show you a little snippet of. And in one of the conditions, mom is talking to the baby and singing, and then she does this, and you guess what she's doing. She's working on her cell phone. And you'll see the response of the infant.
Did you just switch it? Now, for the first time, we can actually visualize functional activity with the MEG machine. Off the baby brain is coming a literal tsunami of data. We can create a movie of the brain reacting as parents talk to their baby.
Oh, he got the bunny.
What really makes us human is the fact that we are social creatures.
Oh, there's more bubbles.
We're proving that babies need social stimulation to learn. The social brain is the gate for learning.
Down.
When Francesca's in front of Lamarcus and she's talking,
The ball clap together.
the motor systems that will eventually be able to talk are activated.
Pia, pia, piano, 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 pia, pia, piano.
But then we have her do something asocial. She looks down at her cell phone. She's not talking anymore. The brain turns off. No auditory signal, no social signal.
So they don't like this condition very well. We'll see how the experiment turns out. But what we're noticing is that even if it's a stranger, we had to take the mothers out of this experiment because babies got too upset. But even with a stranger, the high social activity followed suddenly by a turn away where the baby can't recover the mother's or the stranger's, this is a strange female, can't recover her attention, is a very unpleasant condition for infants when it happens suddenly and unpredictably. Of course, we see this all over the world these days. So one of the signals we've learned that's important, and I just want to mention it quickly, this motherese-parentese pattern, it has a unique acoustic signature. At the top, you see the pitch pattern for adult-directed speech, much like I'm using right now. It's not boring, but it's not what you would use if you're talking to a baby. The one on the bottom, the mother's voice goes all over the place. Can you say, ah? Say, ah. Hey, you. Say, hi. Hi. She's up at 700 hertz there. And this is mothers, fathers, grandparents, siblings. Everybody uses this kind of speech when talking to young children, and it's like an acoustic hook for them. They really listen, they pay attention. When, again, you look at the physics, you can see a little bit why it's a good signal for learning. The small triangle inside, the blue one, is what we sound like when we talk to each other. But when we speak to infants, we stretch it. the E, A, U, universal across English, Russian, and Swedish. And again, our collaborators here, Frasha Lacerda at Stockholm University, was a co-publisher on this paper. All the mothers in all the languages stretch that acoustic signal. It's a bigger, stronger, more separable, more discriminable signal at the time when babies are trying to learn. And sure enough, if you look in parents' and children's homes and you measure at 11 months the degree, the pervasiveness of the percentage of time that someone in the household is speaking Parentese, and you plot that against words produced at 24 months, look at the relationship between dosage, the dosage effect for Parentese. The more Parentese they hear, Motherese, Parentese, same signal, became Parentese when we discovered fathers are doing it as well. So there's a really strong positive correlation. And here, standard speech, the kind I'm using now, it has basically no effect. So every parent should know this, and we're actually coaching parents now in the US to use this kind of speech. And we've shown that when parents increase their use of Parentese, babbling goes up and future language goes up. So it's something that parents worldwide should be aware of. When language is not very present in the environment, there are effects at 5 years of age. Here we have an fMRI study where we're looking at activity in Broca's area. These were 5-year-old children, 5-year-olds. We measured IQ, cognitive ability, linguistic ability, social ability, and we also measured the socioeconomic status of the family. The biggest effect in the study that survived all FDR correction was the family, a measure of the family's economic and educational status. So SES is a proxy for opportunities to learn. And when the opportunities to learn are lower, brain development in the areas related to language and literacy are less active, less specialized. Again, a very important effect for society to understand. So that hearing language is essential. Being read to is essential in that early period. A brief mention of what we're doing with genes. We're just curious about how genes affect learning. And we have not started looking at genes in babies, but we have started looking in kids who are age 19 to 25 who come from China into the United States to become freshmen at the University of Washington. Their language skills suffer and they have a lot of trouble in class. So in the US, they take 3 weeks of an immersive, it's social immersion, 5 hours a day for 3 weeks, where they are just listening to language and talking and trying to sharpen their English skills. And what we demonstrated, we were scanning the kids every day as they're in this class. And there are two very interesting effects. One has to do with the white matter in the superior longitudinal fasciculus, very important to language. What we saw, these are controls who were not yet in the class. These are the experimental kids who are being socially bathed in English. And the FA, which is the strength of that fiber tract, keeps getting stronger with each day they're in class. But when the class ends, it starts shrinking back. So they're capable of learning, but 3 weeks isn't enough, or it's hard to learn at age 20, hard to learn a new language. So you see that feature go down. And these are supporting data, not critical. But here's the genetic effect. So you can see that not all the dots go up. And we did measures on the COMPT gene, and what we saw is that 2 variants of this gene, the MET-val in green and the val-val, show this function up during exposure, down afterwards. But the kids with the MET-MET variant were flat. They didn't show any effect with learning. The brain wasn't growing in this way, in this particular. So it's just interesting that you can see genes push around the effects that experience have on the brain. So we could see in the class that if you measured the pathway, the growth of the pathway, and students' genes, you could predict their outcomes in the class very, very strongly. So again, these are just futuristic studies that will be able to understand not only the beginning state of language abilities, but how kids might respond as they learn. so those genetic differences will be interesting. So I want to end by briefly talking about these. When you know as much as we know now about how language grows in a brain, what children need, you can start to imagine the interventions that are going to make a difference. So one of the things that we're very interested in the United States is to create bilingual babies. In America, there is still the belief that two languages confuse kids, that their primary language will be reduced if you introduce them to a second language. Now, we know from our basic studies that that's not true, but it's still hard to convince. So here's
Other half of the babies,
a
such
basic
as the one
study
in this
that we've
video,
done.
were from Spanish-English bilingual households. Our researchers first prepared the babies for data collection. They used a hat and a special digitizing pen to track the shape of the baby's head. This procedure allowed changes in the magnetic field. It precisely pinpoints both.
Da, 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 da.
a very good baby in this study. So we're in monolingual and bilingual tests, we're looking at the responses to Spanish and English sounds, and you can see, as you'd predict, that the results for monolinguals in red, they're not showing responses by this age, 11 months, to the Spanish, but to English. The interesting thing is that the bilinguals are showing equivalent responses to both Spanish and English, and that the English scores themselves do not differ in the monolinguals and bilinguals. So exposure to two languages does not confuse. In fact, the biggest difference between the two brains, the bilingual Spanish-English kids and the monolingual kids, is activity here. This is prefrontal cortex. What's happening as you learn a second language is the attention mechanisms are getting sharpened. You're developing this ability to switch back and forth between the two languages. You're listening to mothers speak Spanish and dad speak English, and you're kind of toggling back and forth. So much stronger responses. As soon as speech comes on, there's more activity in prefrontal cortex for the bilingual kids. And that is what we think is producing better scores in executive function tasks. So you probably know that all bilinguals are better at controlling their attention and exhibiting cognitive flexibility skills. They're better and more inventive at creating a novel solution to a problem. So are the 11-monthers. So here's a little executive function task, and I'll show you how much better the bilingual child is than the monolingual child. So in this task, you've got a plexiglass box, and it's only open on one side. You hide the toy in there, and the baby's job, they want to, pull it out and play with it. So every child, monolingual and bilingual, solves this problem. They find where the door is open, and they pull out the toy, and they're really good at it. But this is where the hard part comes. When you take the box and move it around, so now the door's open on the other side. So now it becomes a challenge to invent the new solution. And monolingual kids tend to do what this baby's doing, which is to use the old solution, right? Keep looking at the side that used to work, but now it doesn't. So she doesn't pass the test in the required amount of time. Here's the bilingual baby, same first condition, door is open on the left, and a lot of kids push on the box almost as though it's going to pop out, but they can all solve this part. And the question is, what happens? She has to give it back, of course. And yeah, okay. So you'll watch her. She works really hard to get it out, and she looks briefly to the old side, but then she goes right to the new side, right? And she works hard to solve that task. So whether you're 11 months or you're an adult, if you are bilingual or trilingual, you're just better at cognitive flexibility. You are more able to solve novel tasks. So in many ways, it's good for your health. There's less Alzheimer's in bilinguals. There's less cognitive aging in bilinguals. So what's not to like about being bilingual? So if we can convince our Americans that this is true, it will be good. We're working now in Madrid. I'll briefly show. I brought juniors from the University of Washington to the Madrid early education centers. We had an 80-week intervention with 300 kids, 150 in control groups who got the regular bilingual program, and 150 who got our newly invented, based on research, curriculum and method for with parentees and all of that good stuff. And the results were incredible. So at all of the 4 age groups, the red group is our 18-week intervention. And at each of the age groups, the results are really stunning, the degree to which the kids learned and started producing in English. So here's our little graduates. The infant brain is very flexible. Another signal that's missing in a lot of American schools is music. Music and the arts are being reduced because teachers have the belief that cognition and things like music and the arts are operating in separate parts of the brain, and we won't support cognition if we don't give kids more time. This is nonsense, of course, but because things like art and music promote development in broad ways. So we did an experiment, just like the Mandarin exposure. We're exposing babies to music in groups at that magical time between 9 and 10 months. They heard the waltz in many different forms in a social environment, 12 sessions, and they played with instruments that would help them keep time to the beat of the waltz. And then we're tracking language to 30 months of age. And here's what those sessions look like.
Me out to the ball game. Take me out to the crowd.
So what does that do to the brain of the baby? When you compare it to control kids who come in and play, they'd have the same things to play with, but they don't hear the music. So what we saw in the MEG tests afterwards is that you not only sharpen responses, so this is to music, you sharpen responses in auditory cortex, but you also sharpen the responses to the signal differences in prefrontal cortex. So it's as though you're training pattern detection. And it's not only, it doesn't only show itself in music, but also in speech. That you give them a novel speech signal, and again, it's about timing, and the babies in the experimental group who heard the music are better at detecting the pattern shift in speech, and you see it both in auditory cortex and in prefrontal cortex. So as though we're training baby brains to detect patterns in the world. And once you know that there are patterns in the world, I think that infants tend to then attend to those patterns. So that things like music might illustrate to us why the early period is so potent to the baby, because the baby brain is waiting for the architecture to be built in its sensory systems and in its cognitive systems that predict what it's like to live in this world. So we think that all of this work on human learning should lead to an extension from neuroscience to education. And if you think about the foundations for a kind of new science of learning, it's going to be composed of all of the work that's going on in psychology, especially developmental psychology, and in neuroscience, and work in the classrooms about what works. And of this concept of machine learning, I don't know how many in this audience are interested in artificial intelligence and the machine learning groups that belong to them. We're now taking brain data, like the music study. We know we have a neuroscience result. So going at the data in a regular way where you're looking in particular areas, expect to see findings. The machine learning group has no priors. The machine learning group just looks at the data, the tsunami of data coming off the brain, like a pattern detection task. They just look at it to look for patterns, wherever they are, whatever they look like. So we're in process on these studies. We have a very strong machine learning group at the University of Washington, and we think that the future, combining machine learning with neuroscience, is going to be a very interesting way to discover new patterns that we don't know how to predict in the brain, but that machine learning analyses will turn up and lead us in new directions. So just to conclude, I truly believe language is a window into human cognition. It's a wonderful way to see how human brains work. That the infant brain is remarkably sensitive to experience. What Bill Greeno used to call experience expectant, that's what the brain is. The brain is waiting to be wired, and experience is social experience is what's going to wire that brain. So it is experience expectant, social experience. The power of the social brain and the social world of the child, I talk of it as gating linguistic and brain development, that it's necessary. The kids in foster care didn't get that social experience. Social experience opens up systems that, like the language system, to allow it to learn. Music promotes sensory as well as cognitive development. It's a mistake for our schools to remove art and music from their curriculum. And understanding infants' brains, acquiring language will reveal more generally how humans learn. We used to think that language was a special system, that it was modularized, that it was completely separate, that studying cognition and studying language would be as different as night and day. I now think that the lessons coming from the study of language will teach us quite general features and principles about how young brains learn, and potentially help us keep our own brains awake, alive, and learning well into our, who knows, 80s, 90s, and 100 plus. So that's the positive message. And I want to recognize all the way through, as I race through, I don't have time to recognize all the collaborators. It's a huge number of kinds of studies and expertise coming from many disciplines to allow this large laboratory, many methodologies applied. It takes a huge number of people, wonderful collaborators all over the world to do that, and it takes a lot of support. So I want to thank my strong supporters, and thank you for listening. Thank you.